Taking a look at heaps. So what is a heap? Well, a heap is a type of binary tree. So it's a binary tree, which means that it's a tree, it's non-linear, it has a left node and a right node for every parent. But there's a few special things. Well, the first thing is that it is complete at every level except the last. So let's look at an example. So let's look at this, right? So right now, this is the last level. This is the last level. So, and that means that every level before this needs to be complete, but this currently isn't because there's nothing over here and there's nothing over here. But now it is. Now once I've added those two in, now it's complete. Until those two are there, it's not complete, and it needs to have one at every single possible place in that level, except the last one. And then the last one, it needs to be as left as possible. Left as possible. So what that means is that if I put something in here, then this is not a heap because you have lots of spaces here and lots of spaces there. So instead of putting that one right here, what I need to do is um, put it in a better place, which is right here, because that's as left as it can go. I can't put it in there, or if I want to add a new one, I need to add it in here. I need to add it in here. And that's the main thing about a heap. It's complete everywhere, and then it starts from the left. So why exactly is this? Well, one of the main reasons is because heaps can be expressed using an array. So the reason I talked about this earlier, but that's because you can let this be the 0 index, this be the 1 index, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if this wasn't complete, you'd have to kind of jump. You'd have to go from 4 down to 5 here. But that wouldn't really make sense because it wouldn't be easy to tell which is the parent and which is the child. Because it is complete, I know that the children of 3 are 7 and 8. And the reason is because 3 times 2 plus 1 is 7, and 3 times 2 plus 2 is 8. Or 4 times 2 plus 1 is 9, so that's my left child, and 4 times 2 plus 2 is 10, so that's my left child. So I can just store whatever things I have here, 1, 3, 5, 7, 2, 1, 8, etc. 1, 3, 5, 7, 2, 1, 8, just as an array. And I can jump from my parents if I'm at a particular node 3. So this is at index 1. I can just go 1 times 2 plus 1. See that my index here, that should be one child, and that should be the next child. Or I can go backwards too by taking this. If this is j, I can do a j minus 1 and divide it by 2, taking the ceiling of it and then subtracting. Uh, yeah, that should work actually. Minus 1 at the end, sorry, minus 1 at the end. Yeah. There's different ways to do it, but that's the main thing. So I've explained it over here. Sorry, floor j minus 1 over 2 is the right one, or ceiling of j over 2 minus 1. Either of them will get you there. But that's the main idea. You can take a heap and express it as an array. There's kind of one more important thing. In terms of heaps, we actually have two main types of heap that we tend to look at. So we look at min heaps and we look at max heaps. And the idea behind min is parent is always less than child, both children. And in a max, it's that parent is always greater than children. So in this one, in the max one, the largest one of all is at the top. So there's the root. So the root is the maximum. So that means that whenever you store it, it needs to have like 8 here, and then the children need to be 6 and 5, let's say, or something. And then the children of 6 would then need to be 1 and 2, and then children of 5 might be 3 and 4. And this would be a heap. This is a max heap. That's fine. But but you have to sort of enforce these conditions in a way. So by inserting and deleting cleverly, you have to force these conditions occur. And often once you have any sort of a heap, so let's say we have 3 here, and then 5 here, and then 2 here. Now this is not max, and it's not min either. This is just a general heap. So if I wanted to make it into a min heap, what I would have to do is I would have to make sure that the 2 is above the 3. So then I would swap these two. I would put the 2 over here and the 3 over here. And so what that looks like is in my array, since I previously had 3, 5, and 2, is that I would then swap these two elements, 2, 5, 3. And so with heaps, you have to maintain this structure, this whether it's a min heap or a max heap. And so maintaining that structure is the difficult bit, is the bit that requires operations. But once you've maintained that structure, you always know that the min or the max is at the top, and so you can easily use it and extract it easily. There are lots of applications for it that I've talked about a little bit over here. So it's useful for priority queues. Priority queues are when things have a certain priority. So you can kind of imagine, you have a VIP person in your queue that you need to be allowing in front. When you have a queue, but essentially you need to be allowing people that have larger values to come out first before other people. Or when you're trying to do heap sort, we'll talk about heap sort later. But it generally heaps have a lot of different applications. Most of the applications are priority queues. Um, but yeah, they're all around useful as well for other algorithms like Dijkstra's algorithm on shortest path, finding the k smallest element. So instead of just getting the smallest element in a min heap, you can get the second or the third smallest element as well, very quickly. Yeah, so that's like just a brief introduction into heaps. Try out the different activities like by implementing these sort of functions. But yeah, let me know if you have any questions.